Be here in around 30 minutes. Okay, hello everyone. I'll quickly share my screen. Today we'll be going over invariants and monovariants, which are pretty useful concepts in combinatorics. Also, to everyone who sat in Demo 2 yesterday, hope that went well. I think maybe Isabel and Josie said they sat it. So yeah, good luck, guys. Okay, so what are invariants? Let's have a basic overview of them. Oh, right, my camera, I forgot. Um, okay, whatever. Yeah, I'll turn it on. Um, okay, so invariants, they're quantities related to like a game or system, which they never change, right? So maybe you look at some quantity and it always remains at like two or something. Like no matter what you do, this fixed quantity will stay at two. And these things are good because they kind of give some kind of structure to like a game or system that might seem kind of chaotic. Yeah, like maybe you're moving around a lot of blocks or you're changing a lot of numbers around, and it feels like everything's changing. But if you can find one quantity that stays fixed, it tells you a lot about what kind of positions in the game are possible and which ones aren't possible, right? Um, I think it's well, obviously it's good to go through a few examples. So I'll go over the first problem here. So we're playing a game here. Well, not really a game, but we have a process. So we start with a bag with 2024 white balls and 2025 black balls. And we have like this one move we can do. And this one move we can do is we pick out two balls from the bag randomly and we throw them away. Yeah, if the two balls were the same color, we put a black ball back. But if they were different colors, we put a white ball back. And eventually we're gonna be left with only one ball in the bag, right? Because every time you do this move, you like have a net decrease of one ball from the bag. And the question is to show that the last ball must be black. Mm, and I think at first it's a bit hard to approach a problem. I mean, you can try with smaller cases, right? Maybe you can try with like three white balls and four black balls, and that is good to try that. Um, but I think like if you just try small cases, it might not be very enlightening, just because there's no real strategy, right? It's a random process. So it's kind of chaotic. It's kind of weird. You can't really. It feels like you can't really get a handle on why it's true. And yeah, if you do the process, the last ball left in the bag will always be black. But that doesn't really give you any more information because you already told that from the problem statement, right? So this is where something like an invariant is very useful. It gives you something that stays fixed within the system no matter what you do. Um, so I probably won't get you guys to try this for too long on your own, just because I haven't really um like given any examples or like of how to like of what you're actually meant to be doing. Um, okay, I mean I guess okay, I'll give you guys a hint first, and then maybe you can try it out. The hint is something that's pretty common when you're dealing with these types of problems, or a pretty common like concept, right? It's the concept of parity, where here parity is kind of just a fancy word for odd or even, right? So like maybe you can play the game with the smaller balls, but track whether there's like an odd or even number of white or black balls and see if you can notice something. Um, yeah. Okay, so like, does anyone have any ideas? I'll send a Jamboard link in the chat, just so we can work on the problems. Okay, if no one has any ideas, I guess we can we can let's play the game together on this Jamboard. Um, I think I'll make it a bit simpler, right? Let's start with four white balls. I need to write better on my mouse. Four white balls and five black balls, right? And I'm just gonna try simulate a random process here, right? So um, okay, I have my table here showing the number of white balls and the number of black balls. So at the start we have four and five, and I'll track here are my balls, right? Yeah, here are my balls on my bag, and maybe okay, the first move I randomly pick out two balls of different colors, and I think I said that was equivalent to um putting a white ball back in, right? Okay, so maybe I put a white ball back in. Okay, so notice after the first move, that's equivalent to removing a black ball, yeah? Okay, cool. Maybe next time I'll delete two white balls. And this time I add a black ball back in because they were the same color, right? So now we have two white balls, but four black balls. Okay, and maybe now, I get rid of two black balls. I mean, I randomly pick up two black balls. I add another black ball back in. Okay, now it's, oh, sorry, but there should have been two and, oh, never mind. Sorry, there should have been two and five here. And now we're back at two and four. And maybe okay, play this game again. Um, okay, so I'm literally just simulating like random moves at this point, yeah. And we're getting rid of balls one at a time. 0, 2. And then the last move we do, we get rid of two black balls, they're the same color, so we add another black ball back in. Oops, and then okay, anyway, sorry, we're left with zero white balls and zero black balls, right? Ran out, but kind of ran out of room here. But we're left with a black ball, as the problem statement suggests that we should be. So okay, if we have a look at like the number of white balls and black balls that we had throughout this entire process, like is there something that you can notice about? I mean, I gave the hint earlier, right? Parity, like even in oddness. Yeah, great. So it's about that, right? Like if you look at the black balls, I mean, it's kind of weird, right? It's kind of like 5, 4, 5, 4, 3, 2, 3, 2, 1, right? But if you look at the white balls, it feels a bit more calm, right? It feels more stable. It's 4, 4, 2, 2, 2, 2, 0, 0, 0. And especially in the context of parity, it's in particular, it's always even, right? And okay, you might look at this and you want to look at the process and think, is there a reason why it should always be even? And also, wait, I'll just post the slides in the chat. I'm not sure. It's You guys probably got it in the email, but just to be sure, just if you want to have a look at over the questions that we're going over, you can go on that link. Okay. Um, like let's have a look at the two types of operations we can do, right? Like move one, you can like you turn a black ball and a black ball into a black ball, or you turn a white ball and a white ball into a black ball, right? And move two, you turn a black ball and a white ball into a white ball. And if you have a look at these operations, like the first one here, zero white balls turns into zero white balls, right? Two white balls turn into into zero white balls, sorry. And then one white ball turns into one white ball. So the number of white balls either decreases by two or decreases by zero every time. Yeah. In particular, it stays even, but it's like yeah, it always must have the same parity as it did at the start, right? In our case, it started at 2024, therefore it must end at an even number. But remember, at the end, we only have one ball left, right? So if there's an even number of white balls, but there's only one ball, then clearly the number of white balls must be zero, right? Because if it was any larger even number, like two or four, there wouldn't only be one ball left. So we can conclude that the number of white balls must be zero, which therefore means the number of black balls must be one, right? It must be zero and one for the white-black split at the end. Okay, so that's kind of like that's an example of an invariant, right? Something that stays constant throughout the process, which is good because what you can do is you can look at the value of the invariant at the start, and that must be the exact same as the value of the invariant at the end. So by knowing this, like what happens at the start of this process, you get information about what must happen at the end of the process. Okay, very cool. Let's move on to the next problem. So we've added a few more operations. There's four operations now, right? So I'm trying to make a jeweled string with some following rules. So this is just like one long line, not like a necklace, right? A line of jewels. I start with one ruby, and I have four moves I can do. Right? And the four moves I can do is I can add a sapphire gem to the end. I can make a copy of it, like I can duplicate the string and add it to itself. So if I have ruby, sapphire, sapphire, I can duplicate it, add it to itself, and get ruby, sapphire, sapphire, ruby, sapphire, sapphire. I can remove any three contiguous, which means three ruby gems in a line. So ruby, 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 and I can replace that with a sapphire instead. Or I can remove any two sapphires that are next to each other, right? So I have four moves, and it feels like I can do quite a lot, right? Like it feels hard to characterize like every single type of necklace I can make. Like it feels like there's like an infinite number of options almost, right? But the question is asking, is it possible to turn my sorry, not necklace, string. Is it possible to turn my string, which originally starts with one ruby, and make it so it only has one sapphire on it? And again, obviously, like for these type of questions, like the obvious answer, like, it feels like it should be no, because if it was yes, the solution would just be like a sequence of moves, which would be a little boring, right? So it feels like the answer should be no, it's not possible, even though we have quite a wide array of moves we can use, right? It feels like there's a lot of, um, like choice and freedom for what we can do. There's some restriction, which is this, like this invariant, right? Or this kind of thing about the system that doesn't change. That means we can't go from a ruby to a sapphire. Um, I think this one's a little bit trickier. I'll let you guys think about it for maybe like a minute, and then I'll give a bit of a hint. Um, okay, wait, first, I guess one heuristic or one kind of like motivating fact you can use is that all four of the moves influence the number of sapphires in some way, right? Option one, you add a sapphire. Like option two, you can, double the number of sapphires. Like option three, you can add another sapphire. Option four, you can remove two sapphires. But only two of the moves affect the number of rubies in some way, right? Uh, Only moves two and three actually change the number of rubies. So it might be a good idea to focus more on the rubies than the sapphires because it feels more restrictive. Like there's only really two moves you can do that change the number of rubies compared to sapphires. So it's I guess get a hint, right, or a heuristic, like a hint as a result of that heuristic would be to look at the number of rubies and see how they change as you apply these four moves. Okay, like, does anyone have any ideas? Um, like, has anyone noticed something about the number of rubies or like how it changes as you um like do more of these moves? It's actually it's a bit tricky. Yeah, yeah, okay. So Isabel's nicely characterized how you can change the number of rubies, right? Okay. I guess I'll start presenting the solution now. Well, I'll start presenting like the first bit. I won't finish it off completely, right? So I'm just gonna look at number of rubies because if you think about it, right, if you look at the number of sapphires, it's gonna change very erratically. I mean, you can add one, you can like double it, you can minus or wait, add another one, you can minus two. It feels like it should be going like up and down all over the place. So it's kind of erratic, it's kind of crazy, it's kind of chaotic, right? We're not going to look at the number of sapphires because it's too hard to keep track of what's going on there, right? Here, we'll just look at the number of rubies. So we start with one, right? In every move, okay, right? I'll list out the four moves here. Okay. How do each of these four moves affect the number of rubies? Okay, the first move, it adds a sapphire string. So this just does nothing. Okay. The second one, it makes a copy of the string and adds it to itself. Okay, so this one is times two, right? And multiplies the number of rubies by two. The third one, I can remove any three consecutive rubies, right? Okay, so I can minus three. And the fourth one, I can delete two sapphires. Okay, that doesn't affect my rubies at all, right? So really, I have these two moves. I can multiply my number of rubies by two, or I could subtract it. I could uh, like decrease my number of rubies by three. And okay, maybe I can like try this process, right? Okay, maybe I'll times two here. I'll have two rubies. Maybe I'll times two later on. I have four rubies. Maybe I times two even again. I have eight rubies. Minus three, I have five rubies. Minus like times two again, I have 10 rubies, right? Duh, duh, duh. And eventually, I want my final state to have zero rubies, right? Oh, okay, great, yeah. Okay, so Isabel's got it, right? Maybe I'll give you okay, I'll give you guys like 30 seconds to a minute to think about like why this isn't possible. Starting from one and only having these two operations multiplied by two or minus three, why can you never get to zero rubies? Okay. Well, if you think about what it would take for you to get to zero rubies, right? Okay, you kind of want to like minus three a bunch of times, right? Like if this 10 was a 12 instead of a 10, I could minus three four times. I get to zero, right? Um, so ideally what I want is I want some multiple of three, such that I can just minus three a bunch of times and get to zero. So cool. As long as I can get to a multiple of three, I can reach zero. But maybe if you try this process, you think, hmm, it feels like I never get to a power of three, right? And okay, maybe here, you conjecture that you can't get to a power of three, right? So okay, I guess this invariant isn't like a quantity, a number so much, right? But it's more like a Boolean like whatever, right? Like a truth operator. It's like a true or false thing, right? It's like, is it a multiple of three? No, right? It is not a multiple of three, and it never will be a multiple of three, right? That's what stays constant about the system. And the reason is, if you have a not multiple of three, right? Something like one. Okay, I multiply by two, right? I'm just gonna abbreviate this. Okay, right? Like it's still gonna remain in a not multiple of three, right? Like if I have a not multiple of three, right? Something that's common to one or two mod three, and I'm minus three. Well, that's gonna say the same mod three, right? It's gonna have the same remainder of three. It's not gonna be a multiple of three still. So whatever I do, like the number of rubies is always gonna be a not multiple of three, a one or a two. Um, like yeah, exactly right. So yeah, it's gonna be one or two mod three because well precisely because of this argument, right? Because the two operations we can do are too limiting in how we actually change our values mod three. So since the start is a non-multiple of three, but the end is a multiple, right? A non-multiple, multiple. We can never get from the start to the end using only these two, or I guess these four operations, right? So that's yeah another example of invariance being very cool, right? It gives you this like the reason it's so cool is because it turns these super complicated processes like these systems where you have so much freedom where you can like do so much stuff into something that's very simple, right? You're literally just looking at the number of rubies. Like notice how in this entire problem I never had to draw out any actual like configurations of sapphires and rubies and how they like form like consecutive strings and how like I can remove them to like I don't have to worry about any of that and actually visualizing any of it. I've purely focused on the value of the number of rubies and showed that it can't go from one to zero. Okay. We'll have more problems, like more sort of miscellaneous problems at the end, but I'm just gonna get through like the theory first, right? So we have colorings. Um, Maybe you guys have seen some of this. So colorings is they're a specific type of invariant, I guess. Um, what it is you have a certain number of colors. Typically, not typically, very commonly, you just have two colors, right? Maybe it'll be something like black and white, but it doesn't have to be. It could be like blue and red, right? Or one and two. It's just like different like markers to mark different like positions on some kind of board or some kind of grid, right? So a very common one, a very useful one at that is like a chessboard coloring, right? If you look at the colors, black and white on a chessboard, it alternates, in kind of like a diagonal fashion, right? Like if you move along the rows, it goes white, then black, then white, then black, then white. And then if you go up, it also goes white and black and white and black and white. But if you go along the diagonals, it's all the same color, right? Um, and that's good is I mean like I guess a very famous example, maybe you've seen one before, is if you place a domino on a chessboard, it always covers exactly one white and one black tile, which is which is kind of interesting, right? It's kind of useful. And it is an invariant of sorts because in that example, the number of like black squares covered equals the number of white squares covered, right? So that's kind of like your invariant. Like the number of black squares covered minus the number of white squares covered is always equal to zero. But it doesn't have to be, black and white. it could be, black, white, and gray, right? You could have three colors, and it doesn't have to be a chessboard coloring. You could color the first row all black, then the second row all white, or you could color, two by two squares black and white, or you could color like whatever, right? And the hard part of some problems, right, is figuring out how you're going to color your board to give you information. But yeah, ultimately you're trying to select the right number of colors in the right places to give you a useful invariant, which gives you information and like actually helps solve the problem, right? So let's go over some examples. Um, okay, so we have like a 10 by 10 chessboard, right? And in the bottom left 5 by 5 square, we place 25 pawns covering all of the entire like 5 by 5 bottom left corner. And okay, so we can do this kind of like leapfrog move where every pawn uh is able to like jump over another pawn, right? So move two squares in some direction by jumping over another pawn. And it has to land in an empty square, yeah. And you don't like capture the pawn. It's not like checkers, right? You just jump over it, yeah. So the question is it possible to move all the pawns to the upper right corner by such jumps? Ah, well, okay, well, I'm going. Um, okay, well, I'm changing this to 9 pawns, and I'm in the bottom left corner of a 6 by 6 chessboard, just because I don't want to draw a 10 by 10. Okay, sorry, there you go. Actually, here, I'll give an example of how you can use colorings first, right? So the source where I got this problem from is a nice handout by Stefan Wagner from South Africa. It it the question actually originally well the first part of the problem was actually, can you move all the pawns to the upper left corner? So instead of the upper right corner, it was, can you move it from the bottom left to the can you move it from the bottom left to the upper left, right? So if you have our 9 pawns in this bottom left corner, can you move them all from here into there? And I can present a solution to this one, right? As an example of maybe how you would use coloring. So if I color if I just color the board and your typical is there some sticker mark I can use to color this? Hmm. Okay. If you just color it in the chessboard coloring like this, right? Okay, I don't need to color these ones, but I'll do it just for completeness sake. Then if you notice, actually, when you do this leapfrogging move, right? If you go from this where you jump over a pawn, right? Like this, you actually always land on the same color. So a white pawn will always remain a white pawn because it can only land on white squares after doing this move, right? Because you move two in some direction. Like this, right? So we start off with 5 black pawns and 4 white pawns. And no matter how you do these moves, these 5 black pawns will always stay 5 black pawns, and the 4 white pawns will always stay 4 white pawns, right? Um, but if you were to get them all into the top left corner, then you would have 5 white pawns and 4 black pawns, which is not good, right? Because you don't have that. You have 5 black pawns and 4 white pawns. So, like using this kind of chessboard coloring or checkerboard coloring, we can show that you can't get your 9 pawns from the bottom left to the top left corner. But notice that this coloring is actually not good enough for the problem that we want to solve, right? We want to solve the one where it's asking, can we get it from the bottom left corner to the top right, right? This corner to this corner. And if you look at it, yes, there actually are 5 black pawns and 4 white pawns. But okay, I'll spoil the problem. The answer is still no, right? Like a lot of these invariant problems, the answer is going to be no, because there's some quantity in the system that is different from the starting position to the ending position. Yeah. Okay. So if this coloring isn't strong enough, right, we need to find a new coloring, which is like in some ways better, right? This coloring is bad. Like, no, I mean, it's a pretty good coloring. It works for a lot of problems. The issue is it just doesn't work for this one, right? So it's not like some colorings are better than others, right? Different colorings are, suitable for different problems, and this one isn't as suitable for this problem. So I guess I'll redraw my board, and oh god, that is a highlighter. Um, okay, so maybe try find some other coloring. I'll give you a hint. It still is black and white. Where you know a black pawn remains a black pawn, and a white pawn remains a white pawn, but the number of black pawns and white pawns in the bottom left and top right corners are different. Okay, Isabel suggested something. Um, oh, okay, that's different from what I had. Does that work? Um, oh, I think that does work and it's quite nice, isn't it? Yeah, okay. Okay, sure. So actually I'll give the rest of you guys a little bit more time to think about it. But okay, Isabel has proposed a nice solution, alternate solution, not the one I was thinking of. Um and I guess yeah, it shows that there are like there's often more than one coloring that works, right? It's not like there's always only gonna be one. As long as you find one that works, it's fine. Mm. I feel like Jerry should be here soon, but it's okay. Actually, I'll just go over. Yeah, I'll give the coloring now, right? So this is another pretty common coloring. Maybe like the next the next most useful one after the chessboard one, right? It's still two colors, but it is literally just coloring by rows, right? It's like you know this row black, this row black, like black row, white row, black row, white row, black row, right? And if you have a look at it, every pawn after some move, if you start on the black row, you either end up in the same row, or you leapfrog 2 rows up or 2 rows down into another row of the same color, right? So black pawns remain black pawns, white pawns remain white pawns, right? Um, and if you like count the number of black pawns and white pawns in the starting configuration and the ending configuration, you see that we go from 6 black pawns and 3 white pawns to 3 white pawns and sorry, 6 white pawns and 3 black pawns. So, it's not possible to stuff all these like 9 pawns into the top right corner because there's 6 black pawns we need to fit in there, but only 3 black spots available. Yeah. Where black pawns must always stay in black spots. Right. So that's the solution I had. But I guess I'll present Isabel's one as well. It's nice. I think it's probably it's I think it's like the same concept, but it's a little bit more complicated. But it's pretty nice as well, right? It's if you color if you color the grid like this using this one actually is a bit more complicated. It uses four colors. Where it uses a periodic tiling or sorry, periodic coloring every in every like 2 by 2 grid. Uh, oops, not there. And I'll just do like yellow for the last one, right? So we color the board like this. Notice that every like if you look at a blue pawn, for example, it will always remain on blue squares because you always move in this like square-like pattern, right? Like across two, diagonally two, up down two, like whatever two, right? Horizontally, vertically, or oh sorry, it does Isabel want to present it. Okay, yeah, sorry. I'm not sure. Maybe Isabel did want to present, but okay, that's a bit unfortunate. Next time if someone wants to present, please let me know. I'll be more than happy to let you do a bit of my load of the work, right? Especially with Jerry. Okay, Isabel said she didn't want to present anyway. Especially with Jerry not here. Like I need a co-presenter, right? If anyone's offering, right, I'll be more than happy. Okay, anyway, yeah, so blue pawns remain blue pawns, right? They always stay on blue squares. And green pawns remain green pawns and so on, right? But if you look at the start, there's four blue pawns, and if you look at the end, there's one blue pawn. So clearly, again, you're not gonna um be able to fit all the pawns from the lower left into the upper right. And actually, this board's much more colorful, right? Um, okay, let's go to our next problem. Okay, our next problem will require, I think, um, more than just two colors, right? I think it's like a pretty classic problem. It's maybe almost well known, right? But I think it's still a good example of using more than one color in a board. Using more than two colors, sorry, in a board like game. So it's the question is, oh, we have another 6 by 6 board. Very nice, very nice. I'll draw it up here, right? Oh, that's the highlighter again. A 6 by 6, and you have these tiles, and they're 1 by 4 tiles. So it's like the skinny tetronomo. And the question is, can you fully tile without overlaps and without missing any squares, right? Can you tile this 6 by 6 board using only these 4 by 4 tiles? And
Okay, Chris,
again,
can you
I'm
hear
just
me?
gonna spoil it. Holy no, sorry, I was gonna say a bad word. I can't believe this guy's here.
Oh,
Okay,
wow,
and I'm just gonna
thank you.
spoil it. The answer is no. It's pretty obvious if you just try it yourself a little bit. But yeah. The question is why? Hello, Jerry. Hello.
Oh, hello. What problem are we on?
We're on problem four right now. From four.
Problem four. And we're teaching to four students. Sometimes I wonder why we're even doing this in the first place. But then I look at the people we've impacted, and I think it's really great that Mind NZ is having such a tangible impact on so many young students' lives. Like, I think at the end of the day, that's what makes what we're doing so fun.
What are you yapping about? Just shut up,
Like,
bro. You weren't even here for the first 40 minutes. Get out of here.
we might not be able to see their smiling faces and
Don't worry. We're gonna see the
they
Enzima 2
might,
awards. It's all
but
good, bro. It's all
yeah,
good.
I'm expecting some. Wait, Jackie didn't show up. This is shocking.
Yeah, she's graduated. She's too good for this now. Now,
Oh my gosh. Wait, how many did Jackie solve in Into the Mo?
in what?
In
Into the
Into the
Mo.
Mo
I
too.
don't know. I didn't ask. Probably like four,
Yeah, because
right?
weren't the false. Wait. Yeah, because I heard like this other person from Cup solved four as well, and her name wasn't Jackie. So Jackie must have solved five because
What?
she's the goat.
Shut up. We don't even like no, you don't need me talking about this. Okay. Um. Do we just can I just present the solution? I'm just gonna present the solution because I don't.
Yeah, you should
There's
just
nothing more for me
present
to
the
say about this
solution.
problem. Okay. So this is a pretty common coloring when you're using like 1 by n tiles, right? And it's called like a mod four coloring. and it basically works like um I'm gonna use actual different colors, but I think if you don't have like access to colors when you're just doing this on paper, right? Like normally you just write something like numbers in your grids to like represent colors, right? Like should we just do that? No, I'm gonna actually color it because I like
No,
the
no,
colors.
let's do numbers. Let's do numbers.
No,
Okay.
wait, the colors look so nice though.
No,
Wait, I love the
look,
colors though. What?
you're gonna confuse the students. Like, what if they're colorblind?
Huh?
What if one of them is colorblind? Huh? Have you ever thought about that?
Wait, I actually
Like,
didn't think about that. You know, 1 in
yeah,
12 men are
exactly.
colorblind.
Hmm?
You know, 1 in 12 men are colorblind.
No, I didn't know that. What about the statistics for women?
I say 1 in 200.
Oh, only one in
Yeah,
200.
that's like it's so sad. It's okay. I'm not colorblind, so it's fine.
No, but aren't we supposed to be about inclusivity in
Oh
mathematics?
shoot. Mine, wait, mathematical
Yeah, this
inclusion and
isn't gonna
diversity.
look good on the YouTube
Wait,
channel.
okay. If anyone's colorblindness, please speak up.
If anybody who's listening is colorblind, please speak up. We don't care about the people who aren't listening.
Well, if they aren't listening, how will they respond anyway? What?
That's what I mean. You know, like, oh my god, I'm actually getting fired from this job. Like, get ready to
Yeah,
make
you
me
came in
angry.
here and just started disrupting the entire class.
Do I not bring a good atmosphere to this class? Like, Chris, which problem should I do? Can I do problem 5, please? Like, it's the only one I know how to
This is the only one, you only know how to do one problem. You're gone, bro.
do. Wait, I know. I think I know how to do problem 7 as well.
Yeah, because that's like okay, you're done for, bro. Okay, anyway,
Wait,
sorry about the interruption here. Anyway, okay,
wait,
so we have this
wait,
thing. It's
wait,
called
wait,
a
wait.
yeah.
Can you let me present the mango problem? I think it's a really nice problem.
Oh, I literally no, it's not on the slides, bro. I don't think it's a nice problem at all. In fact, I thought it was a really bad problem, so that's why I got rid of it. Because the
Oh.
invariant is contrived, and it's like
It's motivated by the binary problem. Oh, I just spoiled it.
we're not gonna have time for it. I don't like you anyway. Okay. Anyway,
Okay.
sorry guys. Getting back to this problem, right? You can mute Jerry if you want. It's okay. Um, so we have this thing. It's called like a mod four coloring, right? Um, and if you look at it, it's like kind of like these diagonals of the colors, and they alternate with period four. And I guess the reason they call like it's called a mod four coloring, right? Actually, I don't know if it's called multiple coloring. I think I just heard that once. But is if you want to kind of like describe it easily, right? Then if you name your columns like columns like 0, 1, 2, 3, 4, 5, and you name your rows 0, 1, 4, 1, 2, 3, 4, 5, then right let the color in cell IJ be I plus J mod 4. And 0 plus 0, this one's 1, this one's 0, 1, 2, 3, 0, 1. 1, 2, 3, 0, 1, 2. And then if you fill out the entire like table, you get the same coloring, right?
So true.
Where in my example here, blue is like 0 mod, well, it's like the 0 color. And then you know, like yellow is the 1 color and so on, right? Okay, so here I have for anyone who's colorblind but didn't speak up, on the left I have the same coloring except I use numbers instead of colors, right? Okay,
You
anyway,
did
so how
not
does this
need to do
problem
that.
like how does this coloring help, right? This coloring is good because if you look at the 1 by 4 tile and you like overlay it on top of this coloring, like it's kind of obvious that it will always cover one of each color. And it's especially obvious if you use the definition here, right? Oh God, this is terrible handwriting, but um because like uh going across the row or going up a column by 1 increments like the number by 1, therefore like changes the like cycles through the colors. When you have a 1 by 4 tile, like when you start from the left and you go right, you move right like 3 times, you're gonna hit the 3 other colors, right? So you're gonna have 4 different colors every time you overlay some tile, like here, right? Or like here. Okay, so what does that mean? That means that the number of blue tiles we cover up is equal to the number of red tiles we cover up, is equal to the number of yellow tiles we cover up, is equal to the number of green tiles we cover up.
Wait. Low key, let me make a comment.
All right, go on.
Okay, so I think a pretty good name for these diagonals is called looping diagonals, and I think the idea of having looping diagonals, like you see it on some IQ tests, right? Like the IQ test where you have a 3 by 3 grid and you kind of have to fill in the missing square. Like I feel like it's a really common idea on those IQ tests. So like
Okay.
this lesson might boost your IQ by a few points because now you know how to do the
That was
problems.
not a necessary comment.
Wait, and also, this idea also appeared on the 2024 Australian Math Olympiad for problem 4, and I think the like basically I'm gonna spoil the solution. The solution was that you had 2024 different kind of things, and the things were kind of balanced.
Bro, the basis vectors were not the official solution, you
The
idiot.
basis they literally were. Like you're actually lying. The basis vectors were the wait, they were the official solution. You're actually lying. Like,
Bro,
what are
yes,
you talking
official
about?
solution number 8 or whatever. Get out of here. No one used that.
What? No, no. It was literally the official solution from the AMT. Like that was the official solution. And I think the idea of looping diagonals naturally extends to the idea of bouncing diagonals. And yeah, like look at the
No, they
Reddit
don't.
thing.
You're
Okay,
actually
yes, they
talking out
do.
your ass right
Look,
now.
look, look.
You're
Okay,
talking
okay.
out your ass.
Wait. Look at the red diagonals and imagine connecting the squares such that it forms the rectangle. And then that's the looping diagonals, is it not?
Okay,
Am I
well, I'll let
lying?
you edit. Yeah,
Like,
no,
like,
I would never think of that. I literally don't know what you're talking about, by the way.
well, maybe you should have thought of that and had a better solution to the problem.
Maybe you should have
Wait,
fixed it. Okay,
Chris. Look at my 3D printed karamba. Is this not cool? Look.
that's pretty cool. Okay, that's
Look,
pretty cool. Okay,
it's
we're
pretty
not. Oh my
sick.
god, we're not getting through the problems. Okay, cool. Sorry, guys. Okay, anyway, right? Oh my, I almost forgot. We never finished the problem. So, in any state of the game, right? If you look at like after adding any number of tiles, the number of yellow, green, red, and blue tiles that we've covered up will always be the same. So at the end, if we've covered up every single tile, right, without overlaps, that must mean that we've covered up an equal number of blue, green, red, and yellow tiles, right, or squares. Sorry. Um, but let's count how many blue, yellow, green, red squares there are, respectively. Uh, let's count the blue ones. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, let's count the green ones. 1, 2, 3, 4, 5, 6, 7. Oh shit, that's the same. Let's count the yellow ones. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Wait, 10 does not equal 9. So we have 9 blue squares, but 10 yellow squares, which means that at the end, there's always going to be one yellow square left over without a blue square to pair it up with, right? And you can test this, by just playing the game a bit, right? Like maybe I'll
Oh,
tile here, tile here, tile here. Oh yeah, tile here. Okay, put a tile here, put a tile there, put a tile there, put a tile there. Okay, well I messed it up really bad, but
no, Chris, I think you're doing fine.
oh wait, no, that is not a one by four tile. Yeah, there we go. Um, what did I miscount something?
Like
Why
that.
is there a blue and a yellow tile left over? Oh, because I put more
No,
3 by 3
because
tiles.
yeah, you do. Yeah, you do 1 by 3.
Wait, I'm a genius.
So true.
Wait, oh my god, look at this. Wow. So look how there's 2 yellow tiles and 1 blue tile left over. And even if there was another red tile to pair up with this blue and yellow and green, there'll still be another yellow tile left over without a blue one because we said there are more yellows than blues. Great.
So
So
true.
that's like a pretty common way of tiling. I think like a mod 3 tiling is very common as well. Here I had a
Wait,
mod. Yep.
Chris. For the
What up?
Australian Math Olympiad 2014 problems, did you rip off by Conway's? Oh wait, they're literally ripped off by Conway's Game of Life problem.
Oh
Like,
yeah, no, I saw your problem and I remembered this problem, and this problem is like an actual problem. So
nah,
like, so I'd use it instead.
nah, my
Bye bye.
problem is literally the OG because I
Don't care.
stole it from like this random blog on the
Oh my
internet.
god, you actually talk way too much. Okay, we're going to monovariants now, right? So monovariants are like similar to invariants, I guess, right? But it's also some quantity, um, like that's associated with some system, something that like change. Well, it it's different from invariance in that this thing does change, right? So invariance is something that stays fixed throughout all states of the game, but monovariants change. Um, but the difference is they only increase or only decrease. So they either strictly go up or strictly go down. And that's useful because like if something say strictly decreases, but um like let's say something strictly decreases with every move, but it must stay positive, then you know that eventually you can't make any more moves because you can't have it go down while also remaining positive forever, right?
Wait,
Or
so if you think about it,
yeah, so what?
the direction of the decrease is the invariant. So it's basically like the same as an invariant because it doesn't change. You know?
What doesn't what?
Like the direction of the invariant, you know? Because the direction that the invariant goes to doesn't change. So that's the invariant. You
Sure.
know,
Okay. That
you
was
know
okay.
it's
Whatever. Right. Okay. I
continuous.
think all these concepts are pretty similar, right? Invariance,
Yeah,
colorings, monovariance. It's giving structure to a chaotic system. That's like the general idea, right? It's
that's correct.
giving you like useful information and something that like feels like it's quite hard to like have like a firm
Right.
handle on. Mhm.
Wait, are you ripping off my information epiphany?
Dude, I'm not ripping off anything. I'm actually about to end it. Wait, Dawn, can you kick this guy out?
Wait, wait,
Okay.
wait, don't kick me. Don't kick me. Okay,
Okay.
I'll
Okay, so let's have a
cooperate.
look at this problem, right? So okay. So we have a game here. Okay, this is our game, this is our process, right? And we start with hen coins, and the side they show is heads, then
Wait,
tails,
can I
tails,
do
tails,
this
tails.
problem?
What? Yeah,
Could I
you
do
you,
this
you can
problem?
present this problem. I'll be happy to let you present it. You can read it out, you can do everything. Thank you.
Okay, guys. So we're playing a game, 10 coins, and we have heads, tails, 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 etc. And we're choosing a coin which is heads, and then we flip it. But it's not the normal meaning of flip a coin because that implies that it's random. And what we have is that we instead of flipping it, we just turn it over, because flipping is 50-50, and turn it over is like we change its state from heads to tails or tails to heads. So it's not actual flipping, and we choose a coin which is heads, and then we turn it over, and then we also turn all of the coins to its right over. And the source of this problem is actually very interesting. Like, it's a problem from the 2013 movie X plus Y, which is about a British person who participated in the IMO. And, the ending of the movie is that he walks away from the IMO exam to like chase after his math girlfriend or whatever. And I feel like that's unrealistic for two reasons. Because, like, firstly, if I'm at the IMO, I
I'll
am
let you
not
present
getting
for
enough
once. One.
opportunity
Sorry.
to like go get a girlfriend, right? And secondly, people who do math don't have girlfriends anyway. So I feel like I wasn't really able to connect with the person in the movie. They should have made him more autistic. So yeah, just a little interesting side note on the origin of this problem. What are you googling?
Yeah, look at this, brother. You say it's from 2013 IMO shortlist. It's from well, it's definitely earlier than that because it's from
Wait, my bad, Dawn. My bad, Dawn. Okay, wait. Don't just DM me. My bad. Oh, wait, that was an
if you
IMO
actually look at
shortlist
it,
problem.
more interestingly, if you look at the shortlist from 2009, it's actually a New Zealand proposed problem. And you have
What? I thought it was a
2009
British problem.
what?
I actually thought it was the British. Like, I thought it was a problem from the British Math Olympiad. That's
Yeah,
crazy. I didn't.
no, I probably was. I don't think this idea is very
Damn,
like original, right?
that's
But
so
yeah, I
cool.
just want to point it out because New Zealand, very cool, very cool.
Wait,
Um,
the IMO shortlist used to be like that. That's crazy. That's
oh my God,
crazy.
bro. Okay, sure. Okay, just
Okay,
present the problem.
so
Okay,
let's
thank you.
continue. Okay, guys. So now, try playing the game for a bit, and I think you'll find something very interesting because I don't think this problem strictly requires the invariant. Like, the invariant gives a really clean solution because without it, you have to do some arguing about like some things I won't tell you because it'll spoil the problem. But without it, the solution's just a lot harder to write up, in my opinion. So like try and find the invariant. And I think the way you can think about the invariant is try and think about which coins are most important, like which coins impact the most other coins. And
Yeah, the
if
monovariant.
you sure, and the monovariant. And if you think about it, if a coin can impact all of the other coins, then it should be worth more than all of the other coins. Just some food for thought.
Okay,
Okay,
yeah,
so
yeah, sure. Um,
try the problem.
Also, wait, by the way, guys, I know that like I'm not sure if you guys noticed, like, or if you guys um So I get on the email did say the lesson was ending at 6 p.m., which I'm not sure if that had been clarified, but that is a typo. We're going to 5 p.m. only. So yeah,
So true. Wait, 5 p.m. Yikes.
less than 30 minutes. Yeah.
Okay, let's continue. Let's continue. I'll give you guys 2 minutes to try the problem, and let's come back at what's the time? 4:30. Wait, my bad one. That was just a little side note. It wasn't my
Never let this
intention
guy present again.
to demonetize the Binance YouTube channel. Like, yo, that was scary. Wait. You can't cancel me, okay? You can't cancel me.
Oh wait, Jerry cancel party. Let's go, dude. Is it? Oh, he was. Wait, what was he saying? He's saying they should have made them more autistic. No, that's good. He was like,
Yeah, exactly.
because he
It's
no,
it's
he
it's
he
fine.
wanted
It's fine.
like more like
I wanted more
awareness. Yeah,
representation.
in the media and stuff, right? Just because it's not like an
Yeah,
accurate
because I
portrayal, and
felt
it kind of gives.
like I couldn't relate to the guy, because he wasn't autistic enough. Even though I'm not autistic, but I just felt like I couldn't really relate to the person.
Yeah, but if you think about it, I think the movie would have been like a lot worse, done a lot worse, like success wise, if they had like um like given him certain character traits which resembled those of more
Well, okay, so
um
to be
mhm,
fair, I think the depiction of autistic characters in media is actually, I think it's something that's grown a lot over the years. Because if you think about some
mhm,
common TV shows, such as, Young Sheldon, right? That Young Sheldon guy, he's definitely autistic, but it's still popular. And like despite a lot of people making fun of the show, I think it's
mhm,
help to blunt the public perception as of autistic people as someone who's unapproachable, right? And if you think about popular novels such as The Curious Case of the Dog in the Night, that does a really good job of presenting somebody with Asperger's as someone who is human, who is relatable, right? Because he's just lost his dog, and I feel like I feel like it's something that helps all of us to relate to kind of the people around us, and yeah, that's all I had to say.
okay, I think it's been 2 minutes.
Yeah. Oh, I learned something new today.
Mhm.
Okay, so I learned that according to Hegel, the ear is the best. Like how the five senses are sight, hearing, smell, taste, and touch.
Wait, according to whom?
According according to everyone,
Oh, wait, sorry, wait, Isabel just asked, can we finish this game in 2 moves? Turn the heads and then turn the second coin to the left and it will all be tails.
but no, but it's asking if it always eventually ends, right? So it's asking for every sequence of moves, must the game come to an end? Like you found a single sequence where the game ends, which is good. Like that's what you should be doing for a problem, like looking at the small cases, but you haven't proven that every sequence will end. Yeah, just some food for thought.
Yeah, like it will always end. Spoiler again. But
Spoiler, spoiler.
the question is why. Okay. Wait, sorry, according to whom? Okay, no, it's okay. You don't. Okay.
I'll talk about it after we present this problem.
True, true. I think maybe is it time to present now? I don't know.
Yeah, do you guys think you've done enough? Like tell me in chat. And if you don't reply within 30 seconds, we'll kick you out from this meeting because you're clearly not engaged.
You're getting almost actually kicking you out, by the way.
Okay, fine. We're not kicking you out, but we'll be very disappointed. Like, when your teachers, like, when you have a
Shut up.
substitute
Okay.
teacher.
Anyway, I'll give a bit of guidance on maybe how you can approach this problem. Right? Okay, let's just play the game a little bit, right? I think it's always good. Like whenever you have a game, right? Play the game. Except I don't want to write T out 10 times, so I'm just gonna write. I'm just gonna have 5 coins. Okay. Um.
That's what I do as well.
Yeah. So okay. So we do our only legal available first move, which is just flip the first heads. Okay, and then maybe I don't want to end the game immediately, right? I'm trying to prolong the game as much as I can. Hmm. Oh wait. Whoops. This. Okay, and then maybe now I flip over. Okay, I'll put a star to show like which head I'm flipping over every time. Whoops. Okay, so the game's not ended yet, right? But I feel like it's about to end soon. Like, why do I feel like it's about to end soon? Okay, well, I mean, it kind of feels like there's been like a bit of a build-up of like I'll just end it here, right? It kind of feels like the number of like tails on the left-hand side is kind of building up, right? So we got this like cancerous block of like tails that like forms on like the left-hand side, and eventually it just overruns um the entire like sequence, and then you just die, right? Like the cancer has killed you, and like maybe a reason like you can like ask is why, right? I mean, I guess once you have like say two T's at the start, right, the starting block, you you can't ever change that, right? Because the only thing you can do is you can flip heads and you can flip things to the right of the heads. So you're never going to be able to like do anything to this block of two T's at the start once you made it, right? Similar with this block of three T's at the start. Like you're never going to be able to change that once you've made it. So it feels like the number of T's at the start kind of like grow and grow, and then until like you just end up with Oh, okay. Well, so yeah, okay. That's what Isabel just said. Yes, the leftmost coins at T can never be flipped again in eventually end. But then the question is, right? How I haven't shown this as a mono variant yes yet because I've shown that it can't increase, right? The number of T's on the left hand side can't. Oh, sorry, can't decrease, right? You can't remove T's from the left. But why must there always be more T's? Like, why can't there be a situation where there's just two T's on the left forever, and I just flip over coins like on the right hand side, like just continuously without ever adding another T to the left hand side. Um, I mean, I don't like
You
it's
can
kind of
do
weird,
it
right?
like
It's
with induction, you know.
what?
You can like kind of do it with induction.
Yeah, you can definitely do with induction, right? Because it's like I guess you would induct on length n, like any sequence of H's and T's of length n will eventually die, right?
Yeah.
That's definitely one way of doing it, but this isn't necessarily the induction lesson, right? There's like a nicer way of doing it when you're looking at like just killing it in one swoop without needing to induct.
So true.
Do you want to like present the solution, or I mean,
Okay, I got you. So, guys, so remember what I said about how if a coin can flip all of the other coins, it should be more important than all of the other coins. Like, if you think about the leftmost coin, it's not super hard to notice that once you flip the leftmost coin, then there's no more coins to the left, right? So no other coins can flip it back over. So once you flip the leftover coin, you're done for. It's over, right? You can never make that coin hit again. So what this tells us is that, firstly, the leftmost coin should have a value worth more than all of the other coins. And secondly, that's the same thing. I don't know why I said firstly. So you can use lots of different invariants, but I think the cleanest one is to assign weights of powers of 2 to all of the coins, such that the rightmost coin has weight 2 to the power of 0 equals to 1, and then the one to the left, like one coin to the left, it has 2 to the 1 equals to 2, and then it's 4, and then it's 8, and then it's 16. So, wait, Chris, can you like write it or something?
I'm pretty sure I gave you access.
I'm on mouse. Okay, whatever. So let's consider weighting the coins such that each coin has value of a power of 2, and it's increasing from right to left. So what this means is that a coin to the left will be worth more than all of the other coins to the right. And if you think about it, when you flip a coin, firstly, your okay, and our model variant is going to be the sum of all of the weights on the coins which are heads. And if you think about it, once you flip a coin that's heads, right? Firstly, you're decreasing the model variant by the value of that coin. And then what's the maximum you can increase it by? Well, if you flip all of the coins to the right, then you're increasing it by at most, 2 to the n minus 1 plus 2 to the n minus 2, etc., all the way to plus 4 plus 2 plus 1, which is equal to 2 to the n minus 1. So what this tells us is that the monovariant will always decrease on any move. And the monovariant is a finite value, so we'll reach the end in a finite number of moves, because when the monovariant is 0, then it's all tails. Any
Yeah,
pressure.
basically the monovariant doesn't go below 0. It can't go
Yeah.
negative, right?
So,
Yeah, so I mean I guess a motivation maybe, or like a heuristic for thinking about this is like,
I guess,
yeah, like Jay said, right? Coins near the left, they feel more quote unquote important. Like you don't want to flip them over, right? Because if you flip them over, you're kind of like killing off a bunch of stuff, right? So maybe we should be giving them more value, yeah. And that's kind of what we're doing up here, right? When we're weighting them more. It doesn't have to be powers of two. It's just as long as we're weighting like this coin a lot more than this coin, a lot more than this coin, a lot more than like this coin, right? A lot more than this coin. Um, like this weighting would still work, but I have powers of 10 instead of powers of 2. Yeah. Um, because what it means is that like once you like once you flip over a coin, you flip over a quote unquote important coin while like you kill off a quote unquote important coin while like um flipping over some like less important coins that you don't care about, right? So every turn you're killing off at least like well you're killing off, but by which I mean you're flipping over a heads, which is more important than any other coin that you might be reviving on this ride. Yeah. Um. So yeah, actually, I wasn't really listening to Jerry's explanation. I hope that it was okay. If anyone didn't understand,
oh,
or even my explanation's right. If anyone doesn't understand anything, please
yeah,
would
please
be good
drop
to
questions.
let us know, right? Because
Okay, good. So, about Hegel's view on the five
but
senses. So, you know how the five.
we,
Yeah,
we need
yeah,
to
yeah.
introduce the next pro. Yo. We need like
Okay,
you've been
fine.
okay.
Let's introduce the next problem. I've been talking too much.
Yeah, you have been talking too much. I agree. Okay. So this problem is we have a table, an n by n table, so it doesn't really matter, which is good because that means I can draw a small table and no one's gonna care, right? Um, and I can just add however many rows I want. Like I don't have to count it. Great. So we have an n by n table. In this case, it's like a something by something. I don't know. And in each cell, there's either a one or a minus one. Uh, right. Okay. That's my table with my ones and minus ones. And what I can do is I have a move I can do, which is I can just multiply every row or column, multiply every number in every row or column by -1. So turn all the ones into negative ones or the negative ones into ones, right? And what I want is I want at the end of this process, um, after doing a finite number of operations, I want the sum of every row and every column to be non-negative. So here the sum is 1, 2, 3, 4, 5. It's like -4, right? Here the sum is 4. This one the sum is 0. This one the sum is 2, right? Here we have the sum is 0 again. -1, 3, -3, 3, -1, and 1. Okay, right? So clearly right now the sum is like we have some rows and some columns with a positive sum like this one, but we have some with a negative sum like this, right? I guess sorry, non-negative and negative. Like 0 is good, but anything less than 0 is bad. And we want to show that after doing this operation some number of times, we can get all the rows and all the columns with positive, with not positive, non-negative sums of entries. So yeah. Hmm. Maybe yeah. Try finding some quantity related to this system, which strictly increases with every move. Wait, I'm
So
just checking it. Three.
wait, how do you solve this problem? Is it like you just keep on doing it?
Well, yeah, you keep on doing it, but why does it work,
Oh,
right?
that's wait, it doesn't work. Oh, that's
No,
really
well, no,
weird.
no, it
Okay.
does work. It does work.
Oh, so
Well,
it does work. Okay, I see.
well, I don't know. Does it work?
No, show me. Oh, I see the vision. I see what you mean. I see. Oh, wait, that's so true. Wait, that's such a smart solution. Loki. Okay, anyways, have you seen the problem yet? You just
What?
finished it, right? Surely you just finished talking about the problem.
Why?
Did you not finish talking about it? Like,
Yeah,
did
I
you not
did finish. I
like,
present the problem. I'll
yeah,
give you
so let
guys
them
some
do
time
it
to think
now.
about
Let
it.
them do it now. Yeah, time to think about it. Okay, so we'll be thinking about the five senses today. And so you know how the five senses are sight, hearing, taste, smell, and touch, right?
Wait, but
So what Hegel
what about
those
proprioception?
ones don't count because okay, so this is Hegel's theory of aesthetics, and proprioception is the sense of your own body, so you really can't use it to look at anything else, right? So the five senses which we use to interact with the world are sight, hearing, smell, touch, and
What
sight.
about ESP though?
Shut up. That's the seventh sense. Okay, so
The
anyways,
seventh. What's the sixth
what?
sense? Spidey sense
Yes, Spidey. No, the sixth sense is empathy.
is what?
It's empathy.
The hell? It's
No,
like
that's basically
it's just how like the
sight.
fourth dimension is time. Yeah.
Okay, so anyways, so what happens is, okay, so when we interact with the world, we use those five senses, right? So what Hegel says is that actually sight and hearing are the supreme senses. Because if you think about the other three senses, touch, taste,
Wait,
and
touch is
smell,
pretty useful. Touch is pretty useful. Come on, let's go here.
okay, give me a second. You have to interact with the artwork and kind of consume it to experience that, right? Like if you're touching the artwork, it's gonna get degraded over time. If you're smelling the artwork, like it'll lose its scent eventually, right? And if you taste the artwork, then obviously you're gonna freaking eat it. Hegel. Hegel's theory of aesthetics.
What
Okay, so
what?
Hegel. So, anyways, so the reason that hearing and sight are the two superior senses is that they don't degrade the artwork being preserved. No, Hegel. Bro. Hegel, you're tripping.
Yeah, Hegel.
Yeah, yeah,
Yeah,
five letters. Five letters.
yeah, yeah.
Yeah. Are you lagging or something? Whatever. Okay, so anyways, so sight and hearing, they're like the two, the superior senses, right? And
Wait,
okay,
no, wait. How is hearing superior to sense? By the way,
okay, I'll say,
to feeling, to feeling.
wait. No, because feeling, you're consuming the artwork, you're degrading it. Like sight and
Wait,
hearing
wait,
are
wait.
maybe
How are you hearing the artwork though?
like is music not art?
Music. Wait. Okay. Okay. Whatever. Yeah. Okay.
Okay, so what he says is that sight and hearing are easily abstractified because if you think about it,
Wait, but
touch,
would you rather lose your sense of hearing or your sense of touch?
that's a pretty hard question. Like if I lose my sense of touch,
No, you wouldn't. No, you wouldn't.
what do you mean? No, I wouldn't.
No, that's a bad idea. What the hell? You need your sense of touch, bro. What?
No, you don't. Like imagine if you lost your sense of touch, and you know that guy from Lookism.
I don't. I did not read
You
Lucasm.
haven't.
Wait,
Okay, that's messed up. Okay.
bro read
Anyway,
Lucasm
so
just so he could feel
so
bad about
sight
himself.
so sight and hearing are easily abstractified, right? Because touch, taste, and like taste, smell, and touch, they all require you to interact concretely with the world around you, right? So because sight and hearing are so easily abstractified, I think that's why Hegel says that they're the more unique senses and they're sort of privileged among the senses, right? Because you don't need a concrete object to do it. Like if you imagine music in your mind, it's basically the same. If you imagine a painting in your mind, it's like basically the same. And okay, so um, wait. And then he also says that art is an idea state where the human spirit and matter intersect together. Yep. Okay,
sorry, wait. Is this problem like, wait, I just realized something. Is this problem like kind of ass?
yeah, isn't it trivial? That's what I said. Sorry, I didn't
Wait,
say that.
honestly,
That was,
okay, I copy, okay, like, this is like,
I swear, isn't it from the Vikram's Combi book? I swear that's where I saw it.
no, it was, but it was, that one I think had a
No.
harder variation. This is from Stefan Wagner's, Olympiad Combinatorics handout, like the South African
Oh,
guy.
you're
Not
correct.
Olympiad,
Wait,
just
wait. South Africa is kind of a goated country. Like, if you think about it, they have the best girl in Africa.
uh-huh. And then
Yeah.
what else they have?
And then they
They got
also have a
Mather. They
silver
got
medal.
Mather.
They got Mapper. They got the greatest yapper that in Africa. That's crazy. Okay. Okay. Wait. What?
No, no,
Among
wait.
him.
I'm presenting the solution now, by the way. I'm
Okay.
presenting the
Fine.
solution,
Fine.
right?
We can talk about it after the next problem.
Um,
Oh wait, there's 7 participants now. Like I remember it went down to 6, but like I think somebody, they heard my yapping and they must have been interested.
they probably just lagged out, bro.
Yikes.
Okay. Um, yeah, so there's like an issue with this problem, isn't there? No, there isn't. Is there?
What issue? No.
Okay,
Why would there be
no.
an issue?
Okay, so right, the first thing you might want to do, right, you want to consider what your monoivariant is, right? I mean, there's some pretty obvious strategies, right? Like, like one obvious strategy, right, might just be like, okay, well, you take some negative row, right? I'll call a row negative if it has a sum that's negative, right? You take some negative row. Oh, by the way, I'm gonna say positive row for non-negative because I don't want to say non-negative. So zero is positive now. Okay. Anyway, if you take some negative row, you're like, okay, I guess I'll just apply the operation and I'll just flip them all, right? Boom, 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 right? Great. Okay. So maybe you're thinking, okay, that just strictly decreases the number of negative rows until we get no more negative rows, right? And we win. And that's like a good idea. But if, right, if for example, okay, this was a -1, right? And this was a 0, and I suppose this was a -1, right, as well, right? And you apply the same school of thought. You're like, okay, let me just do negative plus 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 plus. This becomes positive, but now you've changed this column into negative, right? And you've like changed all these other columns as well. So it's really hard to just like isolate like one column and like it's really hard to just isolate look at one column in isolation and change if it's a negative or positive row or column without changing the states or the values of every other like column, right? I mean, you must necessarily change the value of all the other columns if you're flipping a row, yeah, because like a row intersects every column at least once. So, oh, it was this? Okay, anyway, so okay, that's not like that's not good, right? Um, one, two, three, four. So maybe you have to start looking around for some other like quantities that you can act as a monovariant that you can analyze how they behave and how they change. And there's not too many that you can actually look at. This is a pretty simple simple game, right? But one of the ones that you can look at is I mean I don't know what else more to say on this. It's just consider the total sum of all the values, right? Of all the mn different values in the mn different squares. So if we look at the total sum right now, it's like it's 0, right? Okay, so I've made it so the total sum right now is 0. But what you notice is that if I switch all of these, if I switch the first column, right? The first row, sorry, right? If I apply switch operation and I change the sum from a -4 to a +4, this strictly increases the sum, right? Because I because before you could sum these and get your sum, but now you've changed one of these terms from negative to positive. Clearly, the new sum has increased. and it's increased by quite a bit actually now, right? Like now it's now the new sum is 8. Okay, and then now what I can do is I can select this negative one, right?
So true.
And I'll do I'll do a switch on this row, and now this is positive. Okay, and now my new sum, right, is is 12. Okay, and maybe there's still some like negative columns or something, right? For example, this column is still -1, yeah, even after I switch all of these. So now I can apply switch here. I apply switch here, and plus, 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 minus, minus here to the positive. And again, I've increased the new sum by 2. Okay. No, I'm not like updating every single column, but just the important idea is that every time I switch a negative row or column into a positive row or column, I am strictly increasing the current sum. Yeah. So total sum, this is the sum of all the squares on the board. Strictly increases. But can it just increase forever? Well, not necessarily can it increase forever. There's kind of like a cap on how big this like total sum can actually get, right? There's a cap because at most, right? Um, the highest that it could like possibly hope to be is every cell in our grid being a 1, yeah? And if every cell is a 1, since there's m rows and n columns, the total sum would be mn at its maximum. So the total sum can never exceed mn, right? Which means at some point we can't select another negative column and switch into a positive column because we can't strictly increase the total sum forever. But if we can't choose a negative column or negative row to increase anymore, that must mean we've run out of negative rows or columns to select. And
So
once we've run out of negative rows or columns, that must mean that every row and every column has a non-negative sum, which is which is precisely what we ended up wanting to have, right? So we can show that we can like quote unquote make the board more positive. That's kind of like the intuition behind what it feels like, right? It feels like this should work because with every step, you're kind of like cleaning the board up, you're making it more and more positive. But this idea of a monovariant helps you to, rigorously it's like solidify what it means to quote unquote make the board more positive, right? It's making this total sum of all the elements in the board higher, right? It's increasing that. That's the quantity that gets increased. And you can show that once it, increases enough, um, it must necessarily mean all the um all the rows and all the columns have a non-negative sum. So yeah, that's very cool. That's I mean, okay, that's mostly what I wanted to end up getting through, right? We go through 2 problems for each of the 3 ideas here. I did have at least 4 more problems left, which is a bit sad. But you guys, I guess, can look at that like in your own time if you want. Actually, wait. Let's go over problem 7 real quick. I think this was a nice problem.
what? Wait, how do you do that one?
How do you do it? It's literally the 2022 C4 like invariant.
Yeah, but it's not 22 C4, so I don't know how to do it. That's so
Oh, you're
sad.
gone. Okay. Anyway, right.
Because
So we have 50 girls are seated in a circle. Again, I don't want to draw 50 girls, so I'm gonna replace this with my own problem, and my own problem is gonna say 6 girls. Yeah.
so wise.
6 girls are seated in a circle. And okay, what they do is you have one girl and she has 6 cookies at the start. Wait, 6 cookies? Coins, whatever. She's got 6 coins at the start. And what she can do is if she has at least 2 coins, or if a girl has at least 2 coins, she can pass them along like this. And after this move, we have the girl, well, she's lost 2 coins, but she's given one coin to each of her two neighbors. And she can keep passing coins along like this, right? So maybe she'll pass some more coins to her neighbors, two, 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 and maybe this neighbor will pass some back along to her, so she gets another coin, but this person loses some coins. Okay, anyway, this process keeps going like right randomly. Well, not randomly, I don't know, how the girls want, right? Um, and since to show that it will never terminate, what we mean by terminate is that no girl can make any more moves. Okay, we are like getting to the end of the time limit here. So I'll quickly go over it, I guess. Yeah, sorry, I won't give you guys too much time for this one, but I just kind of want to highlight this idea because it is a pretty common one when you have like passing things around like a circle, right? Or whatever. Um, so what was I gonna say? Okay, the first thing I want to highlight is before we get to the invariant, what would it look like for a ending configuration? I mean, you can pretty easily see that if every girl has one coin, if the six coins are distributed evenly amongst the six girls, no one can make a move anymore, right? Because no one
Oh,
has two
wait.
coins.
Yes, all right.
But
Oh, I see, I
is
see.
this the only like terminating like configuration? And if you think about it, like the answer is yes. And the reason is yes is suppose not everyone has one coin, right? Okay, what does that mean? That means that like someone must have two coins because well, if someone has more than if everyone has fewer than or equal to one coin, um, then either everyone has one coin or someone has zero coins, which means by pigeonhole, someone else must have at least two coins, right? And if you have at least two coins, you can still make a move. Um, like therefore, the only like terminating position is everyone having one coin. So the question is basically asking us, show that you can't go from the configuration 60000 into 11111. And we're going to try find an invariant that's different in both of those configurations, which would imply that you can't go from one to the other. Cool. So what is this configuration? Okay, we only have one move we can do here, so that's nice, right? Our invariant only needs to be preserved under this one move. And the move is passing a coin. So starting with two coins, passing one coin along here, passing one coin along here. Okay, so what we're gonna do is we're gonna apply some kind of value to each person, right? I know we shouldn't, be assigning like, you know, like values to people, right? But okay, we're giving them some kind of weight. Okay, they're different masses, different you know, numbers, different whatever, right? Whatever, like some quantity associated with each person. Um, but not really with the person, with their coins, right? So maybe this person's coins, they're worth A, but this person's coins are worth B, and this person's coins are worth C, right? So if you want to start with two coins that are worth A, move them to a coin that's worth B, and a coin that's worth C. Okay. So I want two coins worth A to be equal to a coin worth B plus a coin worth C. In this case, our like total coin quantity thing invariant is preserved, right? Because two A valued coins go to a B valued coin and a C valued coin. Um, and if you want something nice, I mean, like often with invariants, what you want to do is you like the simplest. You just want to choose the simplest thing, right? Because that makes everything like easy to work with and easy to deal with and easy to calculate. So I'm just gonna do something like A is like n, B is n plus one, and C is n minus one. So like an arithmetic progression type kind of thing, right? So what that might look like is that might look like coin here, coin A here is worth one, three, coin here is worth two, right? So I'll write it in the middle here, right? Here's its worth. Actually, I'll write it in like red, maybe yellow for money, right? So we see that oh, not like this. Oops, sorry. One, two, three, two, three, four. So we see that two coins worth three can be split to a coin worth two and a coin worth four. And maybe we'll keep going like this, right? So if person two here makes a move, then their two coins worth two get transferred to a coin worth three and a coin worth one. So again, the total cost here is preserved. But um, there's like one small problem, right? Because this invariant is preserved when person 2 makes a move, when person 3 makes a move, when person 4 makes a move, and when person 5 makes a move, right? But it kind of like breaks here because there's a bit of a because since we're in a circle, not a line. When the small number and the like big number wrap around and meet up with each other, when player 1 makes a move, their 2 coins, right, that are worth value 2, go to a coin worth value 2 and a coin worth a value of 6. So 2 goes to 8, right? When 1 moves. Similarly, when player 6 moves, we see that they originally have 2 coins, which are valued at 2 times 6 equals $12 or 12 points, right? And it goes to 1 plus 5, which is 6. We see that 12 goes to 6. But the key thing to notice here is that this is actually like kind of maybe a good thing to notice when you have these like kind of circular wrapping questions is it's still constant mods like mod n where there's n people in the circle. So here it's still constant mod 6, right? So instead of constant, we're gonna use big terms. I mean, I don't know why invariant's even a term, right? Really could just be called constant, right? But it's invariant mod 6. It does not
No,
change.
sounds cool.
Yeah, it sounds cool, right? So if you look at the total value, right? Our total value, which is like let's say we start with all our coins, our 6 coins at person 1, right? Our total value of our coins at the start, right, is 6 times 1, since each of these 6 coins are valued at $1 since they're with person number 1, right? Okay, I'll just say dollars instead of like points, right? Our total value at the start is 6, right? And after every move we do, the total value, it might increase by 6, it might decrease by 6, or might not change at all. But the total value of our coins is always going to be the same mod 6, right? Okay, what happens at the end? Well, at the end, we want, okay, I'll do the ending configuration in red, right? We want one person to have to have 1 coin. Okay, well, at the end, how much money is that? It's 1 plus 2 plus 3 plus 4 plus 5 plus 6, which is 21, right? So we want to go from $6 to $21. But there's a bit of a problem, right? And the problem is, well, we already mentioned it, that the total like cost of all, or the total value, the total dollar amount of all our coins must always stay the same mod 6. Therefore, it can't ever reach 21, right? Because it always must be 0 mod 6, whatever it is. So yeah, because 21 is not 0 mod 6. Therefore, you can't go from the configuration where one person has 6 coins into the configuration where everyone has 1 coin. Okay, cool. Oh, I think problem 8 is a nice problem as well, but Hmm. Okay. Yeah, if you guys, I mean, obviously you guys are free to leave at any time, right? But I guess now like it really is. It's 5 minutes past. You guys
Wait. I still have some stuff to say about Hegel's views of aesthetic perception, though.
maybe we can do the next problem as well then. One,
Wait,
two.
did I explain why hearing was superior to sight?
Superior to sight. You're lying with that one, bro.
Yeah. Okay. So look, think about it, right?
Wait,
Okay.
okay, fine. Okay,
Um,
I'll wait. Okay, wait. Is everyone left? Okay,
no, I
people
think
have not
you're
left.
interested in hearing what I have to say about
No,
the.
I think they really want to solve this next problem because it's a really nice problem.
No. No. Okay, guys. Leave after I explain the Hegel's theory of
Wait, guys,
aesthetic
leave
perception
after this problem.
first.
Okay, try this problem. Okay. So, okay, consider a 2n by 2n staircase, which consists of the squares on or below the main diagonal of a 2n by 2n grid. Okay, so what that means is here we have a size 8 staircase, right? And a size 8 because there's like 8 things on the bottom and there's 8 on the side, right? Okay. Um, and a path is a sequence of distinct squares, every two of which are shared an edge. So one such path might start here, right? And maybe okay, I'll do it in a different color. I'll do it in like red or something, right? Maybe go down here, up here. Um, wait. Okay, so here's one path I made. Here's the second path. Here's the third path. And then my fourth path is very small. It just goes across one like cell, right? So I've split this well, I've like completely covered this staircase, this 8 by 8, well, size 8 staircase using four paths, right? And the question is, for a twin staircase, what's the minimum number of paths I need to fully cover a staircase? Um, this is this uses some of the techniques we discovered. I won't, well, we've covered. I won't say which one. Okay. Yeah. You guys can have a think. If you want, you can leave if you want.
Guys, okay, so hearing is superior to sight because what it allows is a correspondence between the art and. Wait, is that your bed? Can I see your bed?
Hmm?
Can I see your bed?
No.
Oh,
Why?
I don't know. I just wanted to see it. I just wanted to see where the goat sleeps. Wait, what's on your bed? Like, what's the round thing on your bed? Like the round stick looking thing. Like, is it a wooden stick?
Huh? Oh, that might. I think that's just that's an envelope for my school photo.
Oh, can I Oh, wait. Was anybody lookspaxing in the photo? Like, were they doing this?
What? Oh shit, shit, yeah, bro. Wait. Uh, I think. I don't, wait. No, I swear there are some people, man. There are some people.
Hmm?
Like, look at the sky, bro. Look at Rand. Where?
He's so
Where's he?
short. Oh,